All right, welcome back, everybody. People, I am so bummed I am not with you today. Unfortunately, my daughter is sick again, and my father-in-law usually watches her on Thursdays, but he is kind of immunocompromised, so we're trying to keep him a little bit safer. So I am at home with Sadie again. So unfortunately, I cannot be with you guys. I would love to be with you guys. I would love to teach this lesson in person because I'm a nerd and I love this stuff. Um, but unfortunately, I am not. I'm going to try to make you guys like a 30-minute video today, and then I will let you use the rest of the time to work on your Section 2.5 homework. I thought that might be a good idea. I know I was supposed to answer questions about the 2.5 homework, but I think just giving you some time to work. The key is in the binder, so if you want to look at that, that's fine too. But again, I'm very sorry. I wish I could be with you guys today. We're going to finish up the notes tomorrow, so Friday. I know it's for me right now, it's Wednesday. So this is Thursday for you guys. That means tomorrow for you Thursday people is Friday. So we're going to finish the notes up on Friday, and then you can have the rest of the time remaining to work on Section 2.6 homework on Friday. All right. So, okay. All right. Let's get going. So this is Section 2.6. It's called Limits at Infinity. Now, in sections 2.2 and 2.4, we investigated infinite limits and vertical asymptotes. We let x approach a number, and the result was a value of y that became arbitrarily large. Like if you're thinking back, here's what I'm referring to. So if I said, okay, what was the limit as like x approaches whatever this is, maybe -1, and we said, oh, it looks like it's going up to positive infinity, right? We discussed when I said, okay, what is the limit as x goes to -1, right? What we're going to be looking at today is, well, what happens like as I let x keep getting bigger and bigger? Well, what happens if I keep letting x get smaller and smaller? What does it level off to anything? Does it go to negative infinity? Does it go to positive infinity? That's what we're going to be looking at in this section. In this section, we let x become arbitrarily large or arbitrarily small, positive, negative direction. And then we see what's happening with the y value, right? Again, we're still letting x go to something, but now we're going to replace this like -1 with an infinity symbol. So let's investigate that by looking at this function here, this x squared minus 1 over x squared plus 1. Now, as x becomes large or small in this case, this is what happens. Take a look here. Examine this table here. I'm just taking x values and I'm plugging them in, and I'm making those x values become very, very big or very, very small. Understand that it doesn't really matter because I'm squaring it, so positive is really kind of the same thing as negative. So it doesn't really matter because I'm squaring it. It does matter sometimes, but in this case it doesn't. So what's going to happen here? Well, look, as I make x get really, 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 really big, just by the plug and chug method, look what happens. What does the limit actually think we're going to? What does it look like? Well, it looks like it's 1, right? The limit, as I make x get really, really, really big. Okay, how do we notate that? As we bring x to infinity. The limit as x goes to infinity, as we make x arbitrarily big, it looks like the limit of this function, this x squared minus 1 over x squared plus 1, looks like it levels off to 1. Look. Well, what is that indicating here? What am I drawing here? Well, it shouldn't have gone down, sorry. What am I drawing here? Oh, I'm drawing a horizontal asymptote. Remember back when we were looking at these things? These were vertical asymptotes, weren't they? When we were taking our y value and letting that go to infinity, the limits of infinity, the limit as x approaches 1 is equal to infinity, right? We would call those infinite limits. When we had infinite limits, those were vertical asymptotes. When we have limits at infinity, and notice there is a difference here. These are infinite limits. These are limits at infinity when I'm taking it to infinity and beyond. When I take a limit to infinity, that is when I could have a possibility of a horizontal asymptote. So those are my two distinctions there. I could have horizontal asymptotes or I could have vertical asymptotes. The horizontal asymptotes are ones where I would keep making x arbitrarily bigger or smaller. The vertical asymptotes are when I let x go to a number and let it go big. the y value would go big or go small, okay? So what are we saying here? As x grows larger and larger, you can see that the value of y gets closer and closer to 1. The graph of f approaches the horizontal line, y equals 1. It's a horizontal asymptote. And it also approaches -1 as well. We didn't really look at that, but it also does level off the -1 up there as well. In fact, it seems that we can make the values of f of x as close as we would like it to 1 by taking x sufficiently large. Remember, we were talking about making x go sufficiently close to a number. This is now taking x sufficiently large or sufficiently small. This situation is expressed by this limit. The limit as x goes to infinity of this thing is equal to 1. That's kind of like what I wrote up here as well. Okay. In general, this is the notation. The limit as x approaches infinity of f of x is equal to some number L. Okay, some number L. This is our intuitive definition of a limit. Okay. As I make x grow and grow and grow at this function, it's going to level off to this. It's going to have a horizontal asymptote at L. Okay, take a look at some of the examples here. Some weird, wacky function here. It goes down and then comes up, and look, it's going to get closer and closer and closer to some number here, L. Okay, it's a horizontal asymptote to L. I know, watch out here. We might be like, well, did it cross an asymptote? Isn't that not allowed? It's allowed. It's just the idea of an asymptote is going to get closer and closer to some value. It can cross just at a different piece over there and still be a horizontal asymptote. It's never going to cross over at that point at infinity. Same thing here. I'm going to get closer and closer from the top side there. And here, this is kind of an interesting one. Some trigonometric functions do this where it waves and waves and waves and waves and waves. Get smaller and smaller and smaller. It's still getting closer to that value L, right? It's still getting closer to that value. I wouldn't really call that a horizontal asymptote, but that limit is still kind of waving toward that L. Kind of a cool one there. So our definition, we could include what's this different here? Well, there's the negative. That's why that one is different. We could also make it go to negative infinity, so we could make it sufficiently small, arbitrarily small, and it's going to be sufficiently large in the negative direction, and it's going to go to L as well. Okay? So, and we have these ideas of horizontal asymptote. The limit as x approaches infinity of f of x is equal to L, or the limit as x approaches negative infinity of f of x is equal to L. We had those same kind of rules for vertical asymptotes. We said as limit of x goes to A of f of x is positive infinity or negative infinity, then it was a vertical asymptote. So it kind of relates. Just the infinity was over here. Now it's over here. Okay. An example of a curve with two horizontal asymptotes is inverse tangent of x. Think about, what was tangent of x? Tangent of x was like this, right? Oops, I should have moved that up a little bit. Should have crossed right here, but that's okay. But this was tangent x, where we had this, right? So if I invert that, inverse tangent, those vertical asymptotes go to horizontal asymptotes. Where were they? Pi over 2 and negative pi over 2. So those vertical asymptotes become horizontal asymptotes when I talk about inverse tangent, okay? So it can have two horizontal asymptotes. What does this mean? What is this implying? I'm implying that the limit as x goes to infinity, as I keep getting bigger and bigger, what's it going to level off to? Of inverse tangent of x is pi over 2. Likewise, I can say the limit as x goes to negative infinity of inverse tangent of x is negative pi over 2 as well. Okay? So both of those things are true statements because I see horizontal asymptotes in there. Okay. Sorry, you hear pages flipping because I'm just getting those pages in the notes. All right, let's examine it on a graph. Let's see a little bit more what it looks like. Find the infinite limits at infinity, and asymptotes. So notice that those are two different things, right? The infinite limits, okay, the infinite limits are here. Right here, remember, those are kind of like the vertical asymptotes. The limits of infinite limits are here and here. I see two infinite limits. Okay, I can say that the limit as x goes to what? -1 of f of x is equal to positive infinity, right? So therefore, I know there's a vertical asymptote at x equals -1. Okay. Since they both go up, I can say the full limit at -1 is infinity, right? Positive infinity. I can also say down here, the limit as x approaches 2 from the negative is negative of f of x is negative infinity. We also know that the limit as x approaches positive 2 from the positive direction of f of x is positive infinity, but it doesn't matter that those don't line up. It doesn't matter that the full limit does not exist because I just need one of those there to make it a vertical asymptote. So there's also a vertical asymptote at 2. Now, let's talk about the limits at infinity. Limits at infinity. Now, what does that mean? That means, okay, what's going to happen here? If I make x get bigger and bigger and bigger and bigger. So this basically means on the right side of the graph, what's happening? Well, on the right side of the graph, what's it leveling off to? Looks like that's 2, 3, 4. Okay. What does that mean? That means that there's a horizontal asymptote at y equals 4. Oh, there. That was weird. Okay, so let's examine what's happening on the left side of f of x. Well, the left side of f of x, as I keep going over here, look, it shouldn't have crossed that line, but look, at 2, horizontal asymptote at 2 right here. So that means y is equal to 2 as well. Those are my horizontal asymptotes. What are you doing there? What's going on there? Things are going haywire here, folks. Is my video still running? I think so. Okay, good. All right, let's keep it going. Let's keep it going along before my computer shuts down on me or something. I don't know what's going on. Okay, example 2. Find the limits at infinity, both positive and negative, 1 over x. Now think to the graph. I shouldn't have put that close over there. Undo. Think back to algebra 1. What does the graph of 1 over x look like? Well, it's our hyperbola, right? It's got those two tails on there. Right? That's our 1 over x. That's f of x is equal to 1 over x. So what I want to do is I want to say, okay, well, what is this then of 1 over x? Well, let's think about it logically. Whenever we don't understand a limit, let's just plug stuff in. Think about direct substitution here. 1 over infinity? What does that mean? Well, let's put in numbers. That could be like, okay, 1/10. If I put in limit as x goes to 10, let's make that bigger. 100? Oh, stop it. What about 1,000? What about 10,000? Oh my gosh, stop it. What about all of those values? What's going to happen there? Okay. Oh geez, I lost my pen. I lost my little dot. Hope you guys can still see it. 1 over 10,000. What does that mean? That means that I'm going to keep getting bigger and bigger and bigger and bigger and bigger, right? As I go on the right side, I'm going to keep getting bigger and bigger and bigger and bigger in the denominator. Okay, well, what's 1 over a really big number? 1 over a really big number is 0. It's going to get closer. It's going to be a very, 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 very small number, like 1/10,000th. And if I keep going, 1/1,000,000th, 100,000,000th, that's going to get closer and closer and closer as we keep going. That's going to get closer and closer and closer to 0. So we're going to say the limit as x goes to infinity of 1 over x is 0. Do we see the horizontal asymptote there? Hope we do. Let's think about it in the negative direction. The limit as x goes to negative infinity of 1 over x is equal to, well, as I go to the left side, the same thing is going to happen. It's just going to be negative, 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 really small numbers. Okay, well, isn't it still going to go to 0? Yeah, it's still going to go to 0. Okay, so we can say the limit as x approaches infinity of 1 over x, or going into the negative direction, is 0. Now, that's going to help us here. Ooh, I got my pen. We got my little dot back. That's really going to help us here. One thing that we have to look at here, or one thing that I have to tell you guys, and this was in the book, and I have to put it in there. The limit as x goes to infinity, we saw it of 1 over x goes to 0. But if I have 1 over x to the r power, meaning that's any power, 1 over x squared, 1 over x to the third, 1 over x to the fourth, that's always going to equal 0. Okay? Now, how's that going to help us? Well, take a look at this. We've got this some weird rational function. A unique way to solve this is to divide by the highest power of x in the denominator. Okay, what does that mean? Well, here's my rational function. 3x squared minus x minus 2 over 5x squared plus 4x plus 1. So what's my highest power of x in the denominator? X squared. So I'm going to divide every piece by x squared. Mr. Spottleson's calling me right now. Should I pick it up? No, it's okay. Minus x over x squared minus 2 over x squared, all divided by 5x squared over x squared plus 4x over x squared plus 1 over x squared. Let's reduce that down a little bit. That's going to cancel here to just become a 3. Okay, that's going to cancel top to bottom. I'm going to have minus 1 over x. This is going to be, well, that nothing cancels. Minus 2 over x squared. This is going to be cancel 5 plus 4 over x, because one of them cancels, plus 1 over x squared. You know, why can I do this? Guys, understand that all I'm doing here is just, I'm dividing top to bottom. I'm basically multiplying numerator and denominator by 1 over x squared. So it's essentially just multiplying this thing by 1. I'm just manipulating what it looks like. So if I just manipulate it what it looks like, I'm not really changing the value. But now let's calculate the limit as x goes to infinity of this thing. Well, that means that's the limit as x goes to infinity of, well, let's write it out. 3 minus 1 over x minus 2 over x squared all over 5 plus 4 over x plus 1 over x squared. That's really the limit as x goes to infinity. So I'm sorry if this is going to bore you. I'm going to write this all out. Limit as x goes to infinity of 1 over x. I can pull out this constant 2 to make this 2 times the limit as x goes to infinity of 1 over x squared, all divided by the limit as x goes to infinity of 5 plus 4 times the limit as x goes to infinity of 1 over x plus the limit as x goes to infinity of 1 over x squared. Now, why am I doing this? I'm doing this for emphasis here. Take a look at this and this. What is the limit of a constant? As x approaches anything, the limit of a constant is the constant. So what I can say here is this ends up being a 3. This ends up being a 5. Well, what does this end up being? Oh, we looked at that last slide. The limit as x goes to infinity of 1 over x is just 0. So I know that this intuitively is 0. And this up here is the same thing, essentially, because look, we said the limit as x goes to infinity of 1 over x to the r is 0. So the limit is, so minus 2 times the limit as x goes to infinity of 1 over x squared. Well, that's just 0 again. Plus 4 times 0 plus, it's a times, this is a minus up here. 0 here. The limit as x goes to infinity of 1 over x squared is also 0. So essentially, this is like saying 3 minus 0 over 5 plus 0. So the limit as x goes to infinity is 3/5. Now, think back to our Algebra 2 days. Now, I used weird terminology when I talked about this, but think back to our Algebra 2 days, and if I had said to you, where is the horizontal asymptote of this thing? You would look at two things. You would say, okay, if this is a rational function, if it's top heavy, then there is no horizontal asymptote. If it's bottom heavy, if it's top heavy, there's no horizontal asymptote. If it's bottom heavy, the horizontal asymptote is at y equals 0. And if it's equal, again, we learned this back in Algebra 2, if it's equal, meaning the degrees are equal, then you would take the leading coefficient off the numerator and divide it by the leading coefficient of the denominator. So this would be y is equal to 3/5. Ah, interesting here. Okay. So we're using the idea of limits to kind of verify that trick. Okay. The limit as x goes to infinity of all of this stuff is 3/5. We didn't when we were back when we were doing that, we couldn't understand the reasoning behind it because we didn't know the idea of limits. Now that we know the idea of limits, we can calculate all of this stuff and say, okay, definitively, yeah, it is 3/5. Okay. All right, let's make this one our last one here. All right, find the horizontal and vertical asymptotes of the graph of this function. We got f of x is equal to the square root of 2x squared plus 1, all over the 3x minus 5. Okay, now vertical asymptote is going to be very easy to find whenever we're talking about a rational function. The vertical asymptote is always going to be when the denominator equals 0, right? Any rational function, vertical asymptote is when the denominator equals 0. So 3x is equal to 5. So x is equal to 5/3. There's our vertical asymptote. Done, check, done. Now, horizontal asymptote. Horizontal asymptote is a different story. I said for any rational function, you would divide by the highest power in the denominator. Okay, let's do it. So we would take the square root of 2x squared plus 1, and we're going to divide that whole thing by just x. And we're going to take 3x, we're going to divide it by x. And we're going to take 5, and we're going to divide it by x. So that cancels. So the denominator is just going to end up being 3 minus 5 over x. Okay. Now, tricky thing here in the numerator. Tricky thing here in the numerator. What I'm going to do is I am going to take that square root on the top. Now, I can't just bring this x in like this. I can't take 2x squared divided by x. But to bring that in, I need to put a hat over it. And when I put a hat over it, I need to do that. Now, what did I do there? To put the house back on, to put the square root symbol back on, think about this. A square root of an x squared, won't that get us back to x? So if you ever need to put something back inside a square root, what you can do is square it to put it back inside the square root. So I'm going to take x and I'm going to put it to x squared and put the square root of it, because wouldn't that simplify back down toward x? Yeah. Now, how does that help us? That helps us with, well, this is still 3 minus 5 over x. I can now take big hat and take 2x squared over x squared plus 1 over x squared. I can now distribute that x squared to both of those pieces inside and put it inside now. Okay, so that means I've got square root of 2 plus, because that will cancel, 1 over x squared over 3 minus 5 over x. And what I want to do here is I'm actually going to erase this equal sign here. To find a horizontal asymptote, I'm going to make the limit go to infinity of this thing. Well, what does that mean? That means this is going to be, well, the limit here, the limit as x goes to infinity of 2 is 2. The limit as x goes to infinity of 1 over x squared is 0. The limit as x goes to infinity of 3 is 3. The limit x goes to infinity of negative 5 over x is 0. So this ends up being radical 2 over 3. Interesting. Now, what does that mean? What does that imply? That implies that this is the horizontal asymptote at y is equal to radical 2 over 3. Now, understand that we squared this thing here, right? And when we squared it, and when we took that square root of it, remember, whenever you create a square root, you not only have to consider the plus, but you also have to consider the minus. We were only talking about the positive root when we continued this thing on, but what we can actually do is say, oh, I have to consider both the positive and the negative root of this thing. Now, how would we have known that? That's really difficult to know. So what I would suggest you do is you go to your calculator and look at it. Is the horizontal asymptote the same thing on the left side as it is the right side? We algebraically found the right side. Let's check the left side too, just to see. So I'm going to put this in parentheses here. I'm going to take the parenthesis square root of 2x squared plus 1, and then divide it by, I'm going to put parenthesis 3x minus 5. I don't think I need that one set of parentheses up in the numerator. Oh, forgot my 5. Yeeps. Yeep. There. Graph it. Zoom 6 it. Yeah. Looks like I do have radical 2 over 3. Think about radical 2 over 3. That's like, well, what is radical 2 over 3? Square root of 2 is like 1.4 divided by 3, like zero point 0.8 or something like that. 0.8, negative zero point 0.8. Yeah, just above there. Just above. Okay. All right. So we'll make this our last one. We'll do the next one in class. I'll give you some time to work on your homework in class. So make sure that you're staying busy, and we'll continue on with the rest of these notes tomorrow. All right. Hopefully, we're all having a good day. Sorry again. I'm so sorry I can't be with you so long.